Hello Chem 212 students, and welcome back for the second video of this week. In the last video, we ended by talking about the reaction of aldehydes and ketones with oxygen-containing nucleophiles, which can result in the formation of hemiacetals, and then the example here of the formation of hemiacetals within a single molecule by the reaction of the alcohol group with the carbonyl, which is what occurs in the case of carbohydrates. In this video, we're going to begin to talk about other nucleophiles that can attack the carbonyl, the first of these being those that contain a nitrogen atom. And as you can see here in this reaction, what's going to happen here is we're going to have acid as a catalyst for the reaction again, and this is because there will be an analogous type of mechanism, although there will be some slight differences, because we have to consider the fact that the amines that may react here can be protonated by any strong acids, and so that's a consideration. The reaction does require acidic conditions to work. Ultimately, in this reaction, the carbonyl, the carbon double bond oxygen, will be converted to a double bond between the carbon and the nitrogen of our reagent compound. Here, this methyl group here being the methyl group attached to this nitrogen, forming a group that is known as an imine, nitrogen carbon double. So what is the mechanism by which this occurs? Well, first we have the nucleophilic attack by the nitrogen atom. So this is a little bit different than some of the acid catalyzed mechanisms that were described earlier. This is because we can't use a particularly strong acid to protonate this ketone, because it would instead protonate the nitrogen. But the nitrogen here is a strong enough nucleophile to initiate the attack, and then there will be a subsequent proton transfer from the oxygen here, which now has a negative formal charge due to the fact that the lone pair of electrons here now reside completely on the oxygen, 3 lone pairs and bond, thus a -1 formal charge. Therefore, it will grab a proton here from the acid. Again, we said acid is required for this reaction to occur, and this is why it's so that it can protonate. The resulting alkoxide ion will then grab a proton, have 2 bonds and 2 again, thus no charge. However, the nitrogen, when it attacked here, it attacked this carbon. The carbon's now making 4 bonds with no lone pairs. The nitrogen is also making 4 bonds with no lone pairs. And so a nitrogen with 4 bonds and no lone pairs has a positive formal charge to it. So that must also be deprotonated to make the final neutral compound, which will actually, in fact, be an intermediate in this reaction that will go on further to react. And so the conjugate base of the acid here can then go and remove a proton in this equilibrium. Ultimately, we get what's known as the carbonylamine. So carbonyl, alcohol, amine, also amine, attached to 1 carbon. So that's where the name comes. At this point, we now this reaction will continue in a way analogous of the hemiacetal to the acetal. This is analogous to the hemiacetal in the reaction with the nitrogen nucleophile. And in that reaction, it would be the same step here where now the oxygen gets protonated by the acid. And at that point, the formation of the amine occurs when we have the loss of water as a leaving group. So the protonation of the alcohol here leads to an oxygen with 3 bonds and 1 lone pair, thus positive formal charge. And when it leaves as this leaving group here, it can leave as water, a nice neutral leaving group, a very good leaving group, whereas hydroxides are not so good leaving groups. They don't stabilize. They have a negative charge that's not super well stabilized. And so simultaneously, this double bond between carbon and nitrogen is formed. And that means now this nitrogen is again making 4 bonds with no lone pairs, because that lone pair of electrons would making that double bond. And so to become neutral again, it would have to be deprotonated, and it is deprotonated by the conjugate base of that acid that protonated the hydroxyl group there. And then finally, we get a nitrogen with 3 bonds, to a double bond and a single bond, and 1 lone pair, so it has 0 formal charge. And that's the final product, the so-called imine product. And so that's the result of the the nitrogen-containing nucleophile attacking a carbonyl. Now, even though this is happening under acidic conditions, notice that the difference between the the mechanism where the alcohol attacked as a nucleophile with the oxygen nucleophiles, with the nitrogen nucleophiles, we have to be concerned with them being protonated by a strong acid. And so under acidic conditions, the protonated carbonyl will not be the first step in the imine formation mechanism. Amines are bases, so they'll consume the proton. So the ammonium ion here is not acidic enough to protonate an aldehyde or a ketone, but it is acidic enough to transfer the proton to the negatively charged oxygen that occurs in the second step. So going back to the mechanism here, we can see that essentially what happened here was once the nucleophile attacked, we had a transfer of the proton in two steps. Essentially, the hydroxyl group got the proton, or the alkoxide attacked and got the proton, and then a proton was emitted from the amines, from the ammonium ion here. So that effectively means that this proton here on the nitrogen moved over the oxygen. That proton transfer there, then it will not be reversible. Once that alkoxide is protonated, it's going to keep that proton. And so there's a little bit more detail to this mechanism that isn't quite shown, but this is effectively what occurs. For the amine formation, the pH can't be too low or too high. So if it's too high, and then it's not acidic, and this reaction won't be catalyzed by the acid in the way that we saw. But if the pH is too low, then too many of too great of a proportion of the amines will be protonated, and there will be no amines that can initiate that nucleophilic attack. And so the right pH for this reaction is around pH 5. So overall, under acidic conditions, we get that formation of that amine with a if we look for a primary amine here with two hydrogens attached. Now, notice that if we go back to the mechanism here, notice that the last step here is a deprotonation of this nitrogen. But what if there was no proton there? Okay, and that's what occurs if you have a secondary amine. So if you have a secondary amine, you're going to have a little bit different reaction. You're going to get a different product. You're going to get an enamine instead of an imine under the same conditions. And this is because of that last step that I referred to. Remember, that last step was a deprotonation of the nitrogen. Well, what if there's no proton there? So let's take a look at that now. So again, the beginning steps are the same. We have the nucleophilic attack by the nitrogen, the movement of the electrons by a resonance arrow here up onto the oxygen, making it alkoxide ion, 3 lone pairs, 1 bond. We get a proton transfer from the acid. This must happen under acidic conditions. And note that the nitrogen has a positive formal charge due to having 4 bonds pairs. Same thing here. We get a deprotonation, and then we form the carbonylamine. So no difference. The first steps are exactly the same. What differs is what happens at the end. Again, the oxygen here grabs a proton. It's protonated so that it can leave as a good leaving group as water, forming a similar compound to the amine, but there's no hydrogen here. So the deprotonation has to occur on the neighboring carbon. And then these electrons here are shown by a resonance arrow to move up to the nitrogen. So after this is done, the nitrogen has the lone pair that came from this pi bond and 3 bonds, giving it a formal charge of 0. And this proton has been removed, and we have a double bond between carbons. This carbon can 2 hydrogens here, this one having none. And so what differs between the primary amine versus a secondary amine is this last step right here. Instead of the nitrogen itself being deprotonated with its second proton being removed, there will be a deprotonation of the carbon to produce the. So again, for each of these, they require acidic conditions to work because every step in each of the mechanisms involves a step of a protonation. And notice that, yeah, it's again the same steps all the way up to the formation of which the nitrogen is directly deprotonated to form the amine in the case of a primary amine, but in a secondary amine here, we're instead going to get deprotonation carbon produced pi bond next to the allylic to its lone pair. We can have a subsequent reduction of that the amines to produce. So likewise, we had a reduction of the alcohol to produce just an alkane. We can have the reduction of the uh, amines here, assuming that we have a reaction with this hydrazine being NH2NH2. Uh, and so this is a two-step synthesis that converts a ketone to an alkane. We start by reaction with the hydrazine, and we remove water here, and we form the this complex here. Finally, we have a subsequent reduction using strong base and water. Here's the mechanism for that. So the mechanism for the second part, at least, here. The first part is going to be completely analogous to the reaction with another nitrogen as a nucleophile, as we had seen before. But after that, when we have this complex here, it's going to be deprotonated to begin with, and then we have a negative formal charge on the nitrogen. At that point, we can show resonance arrows here. This resonance arrow shows these lone pair being delocalized, becoming the pi electrons here, and then the pi electrons here residing as a lone pair on this carbon, making a carbanion here with 3 bonds and pair. This is extremely basic. Remember REO. When it comes to atoms, we do not want a lone pair on the carbon atom. That really is very, very basic. The corresponding acid would have, conjugate acid would have a pK of 50. This is a hugely basic. So in the presence of water, it's going to deprotonate the water, and we're going to again then bond to one hydrogen here. So this carbon now has 4 bonds, 2 to carbon, 1 to nitrogen, hydrogen. At that point, we have a second deprotonation by the base here. Again, this is here base catalyzed, or base is actually a reactant here, the KOH. This is going to deprotonate this nitrogen again here, and we have a second resonance type arrow here. This time it includes the loss of a leaving group. This is going to be producing for us a triple bond between the two nitrogens, making nitrogen gas, which will leave, and that will drive this reaction forward. Lastly, we have this, when this leaving group, this nitrogen left as a leaving group, it leaves a lone pair of electrons here on the carbon. So it is a carbanion now, and then can take a proton from water, again, super basic here, and we recover the base that was used. Each case that occurs, right? So we have a catalysis by base, protonation of the base, deprotonation of the water, protonation of the base, deprotonation, cover the hydroxide. So note the many similarities between this mechanism and the acid catalyzed mechanism that we have discussed. One thing to note, under acidic conditions, the reactive species have to be either neutral or have a +1 formal charge. If it's got a -1 formal charge, that means it's probably going to get quite a good base, and it's going to get protonated by any acid. And so any species that would actually exist under these would not be extreme. So let's talk about now the reverse of some of these reactions. So we talked about the attack of the carbonyl by an oxygen nucleophile, which will produce an acetal. We talked about the attack of the carbonyl by a primary amine nucleophile to produce an imine. We talked about the attack of a secondary amine to produce a enamine. And now let's talk about the reversals of these. And so in the course of these, water is lost when they are formed. So when they are undone, water has to be added. So this is called hydrolysis, because we're breaking these bonds, and we're going to have water as a reactant in order to do. And this is simply an exact reverse of the acetal formation. The mechanism even goes exactly in reverse. uh, of what the formation of the acetal mechanism be. The acetals will only react with water under acidic conditions. So under basic conditions, this will not occur. It has to be acidic conditions. And again, the mechanism is going to be just the exact reverse of the formation of the carbonyl. Okay, so for example, when or the formation of the acetal, it will go through the hemiacetal intermediate. You'll notice that the first step before was protonation of the ketone, and then we had the attack by the alcohol, and then we had the deprotonation again, and so forth. This is going to be the exact reverse of the formation of the acetal. It's going to be reverse, and the uh, hydration of the acetal and the hydrolysis of it. So we're going to start by the protonation of the ether here by the acid. This has to happen in acidic conditions. And then we have the loss of the oxygen here as an alcohol. The protonation allows it to be a good leaving group, like we've seen before, protonation to make water as a leaving group or an alcohol as a leaving group, because when it leaves, it will leave as a neutral compound, will be the alcohol. And we're going to have a resonance arrow here as well, showing the double bond between carbon and oxygen and preserving that octet on the carbon, but also having a positive formal charge on the oxygen, because after we draw these as pi electrons, this oxygen only has one lone pair and 3 bonds. So now it has a positive formal charge. After that, we have the nucleophilic attack by water and a resonance arrow here showing these electrons going back onto the oxygen to give us a ether group. But now finally, we're going to have the reversal here of the ether turning back into an alcohol to make that hemiacetal. The last step here is the recovery of the acid by the proton transfer. And this oxygen here grabs the proton, and then these two electrons are left behind, producing a hydroxyl group and our hemiacetal, because it also has the ether attached to the same group. Then the next step here is the protonation of the ether group here, so that it can leave as a neutral alcohol afterwards. Then we have again the resonance arrows here showing as a pi bond between the carbon and the oxygen, serving that octet on the carbon, and the loss of a leaving group as a neutral alcohol. Finally, this oxygen is going to have a double bond here and only one lone pair, so that will leave it with 3 bonds and 1 lone pair, giving it a positive formal charge. And then this is, very acidic, negative pKa, very acidic, so it can easily protonate water. Water will grab the proton here, and ultimately have the. So this is the exact reversal of the formation of the acetal. It just requires water as a reactant and acid as a catalyst. Hydrolysis of amines and enamines undergo a very similar mechanism. They go through their respective carbonylamine intermediate as well. So they are simply the reverse, in the same way as we saw the hydrolysis of the hemiacetal be the reverse of the formation of, or the hydrolysis of the acetal being the reverse of the formation of the acetal, going through the hemiacetal intermediate. With these, we see the same reverse mechanism, exactly reverse, going through carbonylamine intermediate as well. For the next topic that they discuss in 19.8, the sulfur behaving as a nucleophile in carbonyl reactions. And when it comes to the sulfur, again, it's going to be able to attack. It's a pretty good nucleophile. It will be able to attack, but the ketone here will be a much better electrophile if it's protonated. But we can also have the attack by the sulfur here, the lone pair on the sulfur. We ultimately get a thioacetal, which is similar to our acetal if we have oxygen as a nucleophile here. We can also have, like we had diols, we can also have dithiols, and we can get cyclic thioacetals. And so the mechanism is going to be analogous here to that of the acetals, the formation of the acetals from the carbonyls. Uh, and there's also a way to reduce and add hydrogen here to the ketone via this mechanism. If we create a thioacetal by the use of a dithiol, we can reduce by a porous type of reducing agent that contains hydrogen atoms inside the pores. It's referred to as rainy nickel, and this will ultimately reduce the thioacetal that's formed to regular alkane, replacing the sulfur atoms with hydrogens. Unfortunately, the mechanism for this is not completely understood, but this is yet another strategy, there among many that we've seen so far now, to reduce a ketone directly to an alkane. Finally, hydrogen working as nucleophiles. So when hydrogen works as a nucleophile, effectively the nucleophile is a hydride ion. So we've seen analogous mechanisms to this as well. We actually discussed this mechanism previously when we discussed reducing agents to produce alcohols in chapter 12. And in this mechanism, we have either lithium aluminum hydride or the sodium borohydride. Now, effectively, according to the mechanism that we see, it's the aluminum hydride or the borohydride that are the functional part of this. Although there is evidence that the cations are also somehow involved in the mechanism, but either way, we use a lithium aluminum hydride and water as a proton source, or sodium borohydride and methanol as a protic solvent there, and we can reduce the ketone here to an alcohol, or the carbonyl to an alcohol. We've seen this mechanism before in chapter 12. It's a simple one. The electrons here come with the hydrogen, so it's effectively a hydride ion here, and as a so effectively what we're doing is we're taking a hydride ion and we're doing a nucleophilic attack right here. The way that's drawn is that it's attached to the aluminum. Electrons go attack. But these are essentially two, I'd say, equivalent ways of drawing this. And then we do a resonance arrow here to show the pi electrons here residing on the oxygen atom. That gives it one bond and three lone pairs, so it has a negative formal charge. And it's quite basic, basic like water. And so it will grab a proton from our acid here, and we will get the protonated alcohol from the left behind, leaving water there. And so we can reduce these carbonyls to alcohols using the hydride ion. Remember that this is going to go, if this is producing a, if for example these two groups here are different groups, this will produce a chiral carbon. And so note that we're going through the unsymmetric, the ketone here that is flat, and so it's equally likely to be attacked from either side by the hydride nucleophile. And so because of its flat shape here, trigonal planar. And so in terms of stereochemistry, you're going to get a racemic mixtures products here. Grignard reagents are also common nucleophiles here. They produce a alcohol that also add on carbon atoms simultaneously. So these are really useful synthetically when you're trying to add carbon atoms and you also want an alcohol group at the end. You can modify the alcohol further. So if you're using a Grignard reagent, remember this is effectively like a carbanion. And so this has a negative formal charge, so it's going to attack in here and then produce this negatively charged oxygen atom, which will then subsequently be, and there will also be a methyl group. And this will then be protonated by the water. We have water in here. Protonation. Drew my arrow wrong. We'll have the proton transfer. Grab this proton and you'll get that reduce carbonyl to an alcohol and also simultaneously add carbon atom. Again, just like before, this nucleophile can attack from either side. So assuming that you have a chiral carbon, which you probably will because you're going to ultimately get an alcohol attached to that same carbon, you're going to get a racemic mixture of products. So that's going to be it. I'm going to go a little bit further into carbon nucleophiles in the next video. And so I look forward to, yeah, I look forward to seeing